There's one more thing I want to tell you about entropy before we move on to a new topic, and this is about the Carnot cycle. So I defined the Carnot cycle a few weeks ago on a pressure volume diagram. It's the combination of an isothermal expansion followed by an adiabatic expansion, then an isothermal compression, followed by an adiabatic compression. So this is adiabatic, this is isothermal, this is isothermal. We defined this cycle as the Carnot cycle last time. If we suppose that this temperature up here, this is a constant temperature, right? This is the highest temperature the cycle reaches, we'll call it TH. And the temperature down here, this is the lowest temperature the cycle reaches, so we'll call it TL. Now I told you this cycle is important because I told you it is the most efficient cycle. It's the most efficient possible shape of cycle that you can choose in a real heat engine. But I didn't prove it, but we can prove it using the definition of entropy, which we've introduced today. So I'm going to state this as a theorem. So I'll just state the theorem today and we'll prove it next time. Okay, we'll prove it next week. Okay. The first one is about what's the efficiency of this cycle. I've got a Carnot cycle between temperatures TH and TL. Epsilon is equal to the difference in temperature divided by the highest temperature, which I can write as 1 minus TL over TH. Okay? That's the first statement of the theorem. And the second statement is, as I said, it's the most efficient. So if I have any other cycle with maximum temperature TH and minimum temperature TL, the efficiency will always be less than that of the Carnot cycle. Okay. So any other cycle with maximum temperature TH and minimum temperature TL will be less efficient. So in other words, the efficiency of any other cycle will always be less than the efficiency of the Carnot cycle. So, as I said, we'll prove this theorem using the concept of entropy. We've got a bit more time, so I will just prove part 1, and then next week we'll prove part 2. Proof 1. Okay. Well, what's the definition of efficiency? The definition of efficiency is it's equal to the work done in the cycle divided by the heat which went in. Okay. Right, okay. So in order to do this, I'm going to have to label this diagram a bit more. Let's call this point 1, this point 2, this point 3, this point 4. Okay. Now, we proved this theorem using the concept of entropy. Over one cycle, the total change in entropy must be 0, because entropy is a state property. So when we get back to where we started, we must be at the same level of entropy. So over one cycle, we must have delta S equals 0 because it's a state property. It's a state property, that means it only depends upon the point, not the path. Now there are 4 stages to this cycle, so I can say therefore change in entropy 1, 2, plus change in entropy 2, 3, plus change in entropy 3, 4, plus change in entropy 4, 1 is equal to 0. But 2 of these stages, namely the stage 2 to 3 and the stage 4 to 1, are adiabatic processes. So these 2, this one and this one, are adiabatic. Adiabatic implies that there is no change in heat, right? That's the definition of adiabatic. No heat goes in and out, but remember the definition of entropy is the change in heat divided by temperature. So if there's no change in heat transferred, then there's also no change in entropy. So because no heat is transferred, there's also no change in entropy. So therefore we can cancel these 2 terms. They're 0. This one and this one are 0. Okay. So therefore we get the result that the change in entropy from 1 to 2 must be equal to minus the change in entropy from 3 to 4. Now, what are these changes in entropy? Well, the change in entropy from 1 to 2, this is defined as the integral from state 1 to state 2, dq over t. But in this case, because it's an isothermal expansion, t is just equal to th, which is a constant. So this is equal to 1 over th times the integral from 1 to 2 of heat transferred. And the heat which is transferred from state 1 to state 2 is simply all of the heat which has gone in to the engine. Right? So this whole thing is equal to the total heat transferred into the engine divided by the high temperature reservoir, the temperature of the high temperature reservoir. And we get an analogous result for the other one. S34 is the integral from 3 to 4 of dq over t. But now we're at the low temperature, so here T is equal to TL. And therefore I can take it out as a constant outside the integral. This is 1 over TL, the integral from 3 to 4 dq. But as I go from stage 3 to 4, I'm taking heat out of the system. Right? This is an isothermal compression, so I'm taking heat out of the system. Therefore, dq is negative, and this whole thing is equal to minus the heat taken out of the system divided by the temperature, the minimum temperature of the cycle. So I can put these results all together, let me do it down here, and conclude that the heat which goes in divided by the temperature of the high temperature reservoir is equal to the heat which goes out divided by the temperature of the low temperature reservoir. Okay, we're nearly there. Over one cycle, the total change in internal energy is equal to 0. So this means that the total heat in and out minus the total work done is equal to 0. Now the net heat transfer is Q in minus Q out. And the net work done is W net. Let's call it double, I think that's what I did before. So this should be equal to 0. And therefore, I get that W is equal to Q in minus Q out. And the last line of equations then, efficiency is defined as the work divided by the amount of heat you have to put in. Using this relation, I can write this as Q in minus Q out divided by Q in. So this is 1 minus Q out divided by Q in. And now I can make use of this equation which we derived here. Let me call this equation star. From this equation, you see that Q out divided by Q in is equal to TL divided by TH. So this whole thing is equal to, making use of equation star, this whole thing is equal to 1 minus TL over TH, which is the result that I wanted to prove. Check. Okay, so this is proof of the Carnot theorem, part 2. In other words, prove that the Carnot cycle has the maximum efficiency. Okay, so I need to prove it's the most efficient. So suppose you give me any heat cycle, anything you like. You're given any heat cycle with temperatures between TH and TL. So that means that the maximum T equals TH and the minimum T equals TL. In this case, we can always choose a Carnot cycle which encloses this heat cycle. Okay, this is most easily explained by a picture, I think. Okay, so we can draw on a pressure volume diagram. You give me any cycle you like. Okay, it can have lots of bumps in and things, it doesn't matter. The only thing that matters is it has a maximum temperature somewhere here of TH, and it has a minimum temperature somewhere down here of TL. This is a representation of any given heat cycle. So it must have some cycle like this. And I enclose it in a Carnot cycle. So that means I choose the Carnot cycle which just touches the maximum temperature here and just touches the side down here. This. And just touches going back up here. This. And just touches going this way as well. So the Carnot cycle looks like this. Remember, this is isothermal here. This is adiabatic. This is isothermal here. And this is adiabatic here. In the Carnot cycle. So you give me a heat cycle, I can choose a Carnot cycle which encloses it and has the same highest and lowest temperatures. So as we've drawn it here, this top line corresponds to a temperature TH, and this lower line corresponds to a temperature TL. Now on this diagram I will denote 4 points of interest. The first are the extremal points of the Carnot cycle. I'll call this one point 1, this one point 2, 3, 4. And the second points of interest are those points where the Carnot cycle touches the heat cycle. So I'll call this one A, this one B, this one C, this one D. Now remember, the definition of efficiency is defined as the net work done divided by the heat that you have to put into the system. So I want to show that by replacing the blue line by the black line, the efficiency is bigger. So by replacing this heat cycle with the Carnot cycle, we increase the efficiency. Okay, so first of all, let's look at this part of the diagram. There are two different ways of going from B to C. We can either do BC, so this is the original heat cycle, or we can do the path which goes B to 3 to C. So as I've written it, this is the original heat cycle, B to C, and this is the Carnot cycle, B to C. Well, because this is a Carnot cycle, as I go from B to 3, it's adiabatic. That means that there is no heat going into the system. So there's no heat going in here, and as I go from 3 to C, I am compressing the system at constant temperature, and that means heat is going out of the system. So from here to here to here, there is no heat going into the system. So for the Carnot cycle, Q in from B to 3 to C is equal to 0. Because the adiabatic part is defined as no heat transfer, and in the isothermal compression, you're removing heat. You're not putting it in. So this is true, and it's also true that the work in going from B to 3 to C is greater than the work along the original path from B to C. Why is this true? Well, remember that work we interpreted as the area inside the path. So the difference in work going along this blue path and along this black path is the area here. So the Carnot cycle has a bigger area, and therefore it does more work. Definition of work was the area of this cycle, of this path in the pressure volume diagram. So we have these two facts. First of all, the Carnot cycle, no heat is transferred into the system between B and C. And secondly, the Carnot cycle does more work in going from B to C than the original cycle. Now, if you look at what this means in terms of efficiency, we've increased W, we've made W bigger, whereas Q in stays the same. Okay? We didn't add any more Q in, so Q in stays the same, but we've increased the amount of work. So W gets bigger, Q in stays the same, and therefore the efficiency increases. So by replacing the original blue line from B to C by the Carnot cycle from B to C, we do more work, we don't input any more heat, and therefore we increase the efficiency. Now an exactly equivalent argument works for the next stage, from C to D. So C to D versus the Carnot cycle C to 4 to D. Okay. And again, the Carnot cycle, no heat is transferred in over this part of the cycle. And again, it does more work. It does more work because it has more area in this diagram, right? It's the difference in work done again. So it's exactly the same as the path from B to C. You don't put in any more heat, but you do more work. And again, we must therefore increase the efficiency. So what I've shown so far is that taking the original blue cycle and replacing the bottom part, that's from B to D, with a Carnot cycle, we increase the efficiency. So from replacing this bottom part here by this black line here, we increase the efficiency. So now I need to show also along the top part, we at least do not decrease the efficiency. So replacing this top part of the blue line with this black line also can only increase the efficiency. So next we'll consider the path which goes A to B versus the Carnot path which goes A to 2 to B. Okay, now this one is slightly more tricky because in this stage the heat is going into the system, right? As I expand at constant temperature in the Carnot cycle, heat is going into the system. So it's no longer true that Q equals 0. But we can still show that efficiency must be increased by the following argument. The change in energy along the original path from B to C must be equal to the change in energy along, original path from A to B must be equal to the change in energy along the Carnot path from A to B, because energy is a state property. So this must be true. And the first law of thermodynamics tells you that this is Q from A to B, the net heat transferred, minus the work done from A to B. And this should be equal to Q A along this path minus the work along this path. And along the Carnot cycle, in this case, heat only is transferred in, so there is no heat transferred out, whereas along the original path, heat may be transferred in and it may be transferred out. So I can rewrite this as QAB in minus QAB out minus WAB. And this is equal to QA2B in minus WA2B. This. But this is something positive, so therefore this difference, I can write it in the following way. QAB in minus WAB must be less than or equal to QA2B in minus WA2B. Now we can rearrange this equation and we get the result that WA2B minus WAB divided by QA2B in minus QAB in must be positive. It must be greater than 1. Okay. Right? So this must be greater than or equal to 1. What does this mean? This means, again, by replacing the original cycle by the Carnot cycle, we increase the ratio between W and Q. In other words, as the efficiency is defined, we increase the work by a certain amount and we increase the heat by a certain amount. But the ratio of the two is greater than 1, and again, therefore this must increase the efficiency of the cycle. But the fact that this is greater than 1 also tells you that the efficiency increases. Sorry, I've made an error. I made a mistake here, right? This is something negative which we take away. So if I get rid of it, this thing must be greater than or equal to that. Right? Sorry, this is correct. This is correct as well. That's also correct. Okay. Right. Okay, so the final stage we haven't considered yet is the stage from D to A versus the stage from D to 1 to A along the Carnot cycle. And for this stage, the argument is exactly the same as the stage from A to B. So change in internal energy from D to A is independent of the path you take, so this is therefore true. So therefore Q dA minus W dA is equal to Q d1A minus W d1A. And from exactly the same argument that we used last time, you can show therefore that the work done by the Carnot cycle, the difference in work between the Carnot cycle and the original cycle divided by the difference in heat in between the Carnot cycle and the original cycle must be greater than or equal to 1, and therefore in turning from the original cycle to the Carnot cycle, we have increased more work more than we've increased the heat in, and therefore we've increased efficiency. So that completes the proof. We've shown that along every stage of this path, from A to B to C to D and back to A, replacing the original path with the Carnot cycle must increase the efficiency along every stage. So therefore, replacing the original cycle with the Carnot cycle increases efficiency along every stage of the cycle. So that every stage A to B, C to D, back to A. And therefore, the Carnot efficiency must have maximal efficiency. Okay, and that completes the proof. We started with an arbitrary cycle and I showed that by replacing it by a Carnot cycle between the same two temperatures, we must increase the efficiency.